Let us continue with the second benchmark case, the hopper discharge case. Again, we start by summarizing the simulation parameters. The geometry consists of a narrow slice of a hopper. The depth has a length of 3 particle diameters and the width 20 particle diameters. Note that there are also walls at the front and back that are not shown here on the right. The depth of the hopper is 60 particle diameters, and after the discharge region, a region with a length of 2 particle diameters is simulated. The opening has a width of 6 particle diameters, and we apply gravity in the negative z direction with a strength of unity. As you can see here at the bottom right, the region of interest for the stress monitoring that we do has a height of 2 dp and is located just above the opening. Particles are essentially the same as in the uniaxial case, with the exception that the stiffness has been chosen based on an allowable typical overlap of 2% of the particle diameter. This is based on an estimate of the stress at the bottom, yielding a Young's modulus of 25,000 Pascal. Initially, 3,000 particles are filled into the hopper, and once they are settled, the discharge process is started. We can now immediately proceed to the results of our hopper flow simulations. First, we show a qualitative analysis of the velocity of the particles in the hopper. The video that you see here on the left has been generated with data from the LMGC90 simulator. As can be seen, the particles slide down the hopper, and the simulator is able to simulate also densely packed regions and the rolling of particles towards the outlet at the very end of the discharge process. So here you see now how the particles are rolling here. We have analyzed the remaining mass in the hopper as a function of time and have fitted a linear relation to this data. As you can see, this linear fit is perfect up to times of approximately 110 seconds, and its slope is minus 13.52 kilograms per second. Looking at the performance metrics, we see that the LMGC90 simulator requires approximately 7 hours to simulate the full discharge process. 81% of this time is spent for the fourth iteration, stressing that for comparably dense flows such as the one in our hopper, this iteration takes truly a lot of time. We now consider the results of the light simulations, which are shown here at the top right. Clearly, the qualitative results are the same, and the linear fit is also suitable. However, if we look at the slope, we see a somewhat faster discharge rate of minus 16.78 kilograms per second, which is a plus of 24% compared to the LMGC90 simulation. Again, considering the performance metrics, we note a significantly shorter simulation time of just 90 seconds for both filling and discharge on one CPU. This is by a factor of 280 faster than LMGC90. Of course, LIGHTS has the particle stiffness as an input parameter, and simulations using stiffer particles would require smaller time steps and hence longer simulation times. Since the time step is proportional to 1 over the square root of the Young's modulus, 10,000 times stiffer particles would require a 100 times longer simulation. More results for the hopper case are shown on this slide. Specifically, we now look at the per particle pressure evaluated with data from the light simulation tool. This pressure is evaluated in a small box of size dB cubed surrounding each particle. Qualitatively, we see that the pressure fluctuations are strong and also force chains are clearly visible. Along these force chains the pressure is high, while in regions in between the chains the pressure is low. A quantitative analysis of the maximum overlap here on the top right reveals again very fast dynamics. We also see that initially the time averaged maximum overlap is around 50% higher than the 2% that we anticipated. This is simply because we have chosen the stiffness based on the expected hydrostatic pressure, which is not exactly what we get. Towards the end of the simulation, the overlap gradually decreases as the simulation progresses because the stresses in the packing simply drop. More interesting is, however, the pressure in the bottom region, which is shown here on the bottom right. Again, this pressure fluctuates significantly in time and features a slow temporal decay. This highlights the need for a careful temporal averaging, thus with a frequency high enough to capture the fluctuations and over a time interval that is short enough to avoid smearing out the slow transients here. Interesting is that also the value of the pressure, given the simulation parameters, we would expect a hydrostatic pressure of approximately 24 Pascal. However, as you can see, not even 6 Pascal are reached on average. The reason for this is the lateral wall. Since the simulated domain is relatively narrow, we heard about this, that it's only 3 particle diameters wide, friction occurring at the lateral wall is significant and reduces the stress level substantially. Well, this is it for this section. I hope you enjoyed it and you are ready for the next task. And this is get your hands dirty and try to simulate those benchmarks. You will find the setups and all other details in this section of the iMooX course. To round up our section on benchmarks of the DM simulators, I would like to present some other recently published benchmark simulations to you. Specifically, this is work done by Dosta and a large group of other researchers that was published just recently. A representative figure out of their excellent publication is shown here on the right. As you can see, they simulated segregation of a binary particle mixture in a drum, for which it is anticipated that the smaller particles, here in blue, migrate towards the center of this flow, and the larger red particles stay at the outside of this flow. As you can see, all the simulators predict this behavior and there are only minor qualitative differences. A more quantitative analysis of these differences is shown here on the left, where again it is visible that there are only marginal differences between the predictions at most. We note in passing that also other benchmark cases unveil that all of the investigated simulators, all using soft sphere DEM, agree very well in their predictions. Clearly, there is now a broad consensus on the models and their implementation details of such simulators. We can thus progress to look at other important benchmark criteria, which is the calculation performance, for example. The corresponding data is summarized in this table, in which the simulation duration in minutes is provided for simulation codes when running on a 12-core conventional CPU in multi-threading mode. In the small table on the right, the simulation duration for 2 GPU-based codes is provided. As can be seen, the GPU codes are significantly faster. However, this is a bit unfair since GPUs have thousands of computing cores, and nowadays multiprocessor clusters are available that may use several hundred cores in parallel and not the 12-core CPU used in the present benchmark here on the left hand side. Anyhow, GPUs offer an excellent performance in a compact desktop system, which is what engineers in practice are often looking for. Also, we see significant speed differences between individual codes, which has several reasons as nicely discussed by Dosta et al. Another important detail of this result table is that the relative performance strongly depends on the case studied. For example, for case 1, silo discharge, the ratio of the slowest CPU code to the fastest CPU code is 7.2, while the fastest GPU code only required 3.7% of the time needed by the fastest CPU code. Instead, for case number 3, the big particle impact case, the differences between the CPU codes is much larger. Look at that, i.e. 18 in this case, and the GPU to CPU comparisons show a more moderate advantage, i.e. only 5.7% of the time is needed by the GPU compared to the fastest CPU code. This is it for this benchmark section. I hope you liked it, and we now shift our attention to the last benchmark case. And this is a very interesting one since it compares hard sphere DEM with soft sphere DEM. Specifically, the authors considered the flow in a riser. A riser is a gas particle flow that is relatively dilute and in which particles are transported upwards with the gas. To remind you of the differences of these different DEM simulation approaches, I have indicated the sketch here on the right, which was taken from the publication of Ramirez et al. The key message from this publication is that both codes deliver essentially the same results, which are very close to the experimental data. Here you see contour plots of the local particle volume fraction, which was denoted here with phi s, S for solid. We will see later additional performance metrics which show that the codes have comparable computational expenses over a wide range of operating conditions of this riser. It is now time to finish this unit with an overall summary. First, we have seen that the evaluation of continuum properties like the voidage or the stress can be done on a per particle or on an Eulerian basis. For the latter, we need a weighting function that is required to map per particle properties to the Euler grid. There was no need to discuss this mapping function in detail, as these functions are now relatively standard and have been explored quite well. The calculation of these continuum properties can be extremely helpful, for example for the identification of force chains or for the comparison with simple estimates, like the hydrostatic pressure in a silo. Also, translating DEM data into continuum properties is essential when talking with theory experts. Speaking the same language is important, as even the way we average over particle information is a non-trivial operation. Next, we have seen that calculating the local deformation is a quite complex task. It involves the prior calculation of the contact fabric and the subsequent multiplication with a dyadic product that involves the displacement at the contact. We have circumvented this complexity by looking at global deformations only, which are much easier to interpret. Following this, we also had a short but important look at the boundary conditions that can be applied in a DEM-based simulation. Progressing further, we even had the chance to look at so-called non-smooth DEM, which is an elegant method that allows us to simulate a limiting stiff particles scenario, which is simply infeasible with classical soft sphere DEM. However, each advantage comes with a drawback, and this is also the case for non-smooth DEM. It has certain restrictions. For example, we can only simulate stress-controlled cases with confidence, and the method failed in our uniaxial compression case that was deformation controlled. Also, the computation times were 2 orders of magnitude larger than a classical soft sphere DEM simulation using relatively soft particles. Sticking with the topic of softness, we have seen in our benchmark simulations that the stiffness of the material has a pronounced effect and also sets the number of time steps and consequently the computational expense. Fortunately, we have seen that rescaling with the Young's modulus can help to mitigate this issue. Finally, we have seen from literature data 2 things. There are significant differences when looking at the performance of DEM simulation codes. However, the predicted results are almost perfectly on top of each other. Finally, we have also seen from the very recent publication of Ramirez et al., as displayed here on the top right, that the soft sphere and the hard sphere DEM have a quite similar computational performance, and that in denser flows, which correlate here to lower gas velocities UG in the graph, the soft sphere DEM, the orange curve, has a clear advantage when it comes to computation times. These are good news for researchers that have developed soft sphere DEM codes, as the decade-old myth that this approach is slow in dilute flows is often not entirely true. This happy end for the soft sphere DEM also closes this session and this unit. I hope you liked it. See you next time.